In this assignment of Class 4, we're going to look at a mixing tank shown here. And we're going to discuss a species and an energy balance and how that relates to the dynamic concentration and temperature within the tank. As I alluded to before, we're going to use both a species balance and an energy balance to be able to derive those concentration and temperature response values, or those changes. First thing we'll do is we'll use some constants about our tank. We'll list what we know first. So we have a volume of 100 cubic meters and an inlet flow rate of 100 cubic meters per hour. So go ahead and we'll write those constants down and we'll use those later. Next, and I'll go ahead and I'll make this a little bit bigger just for fun. Go down, we'll discuss the species balance first. So we have some initial conditions. I always find it's good just to write everything that we know first and then go from there. So we have initial condition of no concentration of A, feed concentration of 1, and feed temperature of 300. And we likely won't use that for the species balance. We'll also initialize a time interval. I just labeled that time. And it's just a linearly spaced array of from 0 to 10 hours with 101 points. Next, we're going to create a function to model the change in concentration over time. And I'm going to use ODE45 to simulate that change in concentration. So let's go ahead and let's look at our function. But first, let's look at our let's look at our function. We'll do the energy balance second. So here we have our material balance function right here. You'll see that we have the tilde for the time because our differential concentration doesn't depend on time. We also have concentration, which is what's changing, what's being integrated. That's that second argument. And we have three other arguments. Two of those, the Q, which is the volumetric flow rate, V, the volume, and CAF, the feed concentration. So the reason we do that is just so that this function is as flexible as possible. So we can give it any volumetric flow rate, any volume of the tank, and we're able to calculate what the differential concentration per time will be. So you can see we have our dCA dt as our output of this function, change in concentration per time once again. And you can see that formula. We have volumetric flow rate divided by the volume of the tank times the difference in temperature concentrations, difference in concentrations of what's coming in, times the difference in concentrations of what's coming in. And that's all there is to this function. So let's go up and let's look at how we use that with ODE45. Should be somewhat familiar now. We create an anonymous function here using the @ symbol, and then the two arguments, time and y, which ODE45 requires, and then we input that into the material balance function we created with T, Y, Q, V, and feed concentration in there. And we pass time and the initial concentration to ODE45. Those results are output to those variables on the left, T and Y, and then we plot those results. So let's go ahead, now let's make sure that we're running everything. Let's go up here and we're just gonna run in advance and we'll see what our graph ends up being. So we can see here, we start at concentration of 0 and then we approach 1. It looks like we hit 1 at about 6 minutes in. So that makes sense. We're not going to have a concentration of anything other than 1 eventually, as we're feeding in 1, a concentration of 1 I should say. Eventually that's going to reach steady state and we're going to get what we're putting in. So that makes sense. Now let's add an energy balance and let's look at how we'll model a system with more than one change going on. So here we have what that graph should look like and some hints as you're doing that the first time. Hopefully you looked at those rather than the video first. And here we have our energy balance. So our goal here is to implement this additional energy balance equation and simulate a feed temperature change from 350 degrees to 300 degrees. So initially we have initial concentration of 350 degrees Kelvin, and the heat capacity does not depend on the concentration of A, and that's nice because we have some mitigating variables. We have some multivariable calculus that goes on. So if we can make simplifying assumptions like that, that really helps. So again, the first thing I'd like to do is just list initial conditions. So we have initial concentration of 0, initial temperature of 350, and we have I0, which just is an array that holds both of those. And you'll notice it's a column vector, it's a column array, it's vertical with those semicolons. And that's because we have multiple arguments. Once again, with ODE 45, it requires that. Then we have our feed temperature and our feed concentration, and finally our time interval over 10 minutes. Let's go ahead and let's look at our mixer function now and how that works. Again, we don't explicitly rely on time. So time here is just a tilde. We have y, which is the vector that holds both change in concentration and change in temperature down at the bottom. We say output is equal to that differential, and then y is our input. It's what actually those values are, the concentration and the temperature at any given point. You can see that we unpack y on lines 60 and 61. Then we have some other arguments, Q and V like before, and then we have the temperature of the feed and concentration of the feed. And again, that just allows us to be flexible. Any size tank, any flow rate, as well as any feed conditions, and we can use the same function for all of those. Our differential concentration and temperatures look very similar in their equations, and that's because these are just balance equations, and we have the same heat capacities and similar conditions in our in and our out, so we can simplify this energy balance quite a bit. So let's go ahead and let's look at this implementation one more time in the graph. Here we'll simulate the mixer with ODE 45, again an anonymous function, and then passing all those arguments we use within the function. Our time array and our initial conditions, again that's a column vector using the semicolons, so it's in the same form as what's being output in ODE 45, and in the mixer function as well. Finally, we'll plot our results using a subplot, and that subplot will use 2 rows, 1 column, and then we use the third argument there to signify which figure it is. So subplot 211 will be 2 rows, 1 column, figure 1, and then the second will be the second figure. So here we're going to plot both the concentration and the temperature. Let's go ahead again, we'll run that and take a look at what happens. So here our concentration goes to 1, just as before, and our temperature goes from 350 to 300 after that change at time 0. That does that for this equation, or this, that does it for this assignment. Please let me know if you have any questions down in the comments, and good luck on the next temperature control lab assignment.